This is version 0.1.38 of SynthMaker, which is now available on test flight. I'm going to open it and load a schematic that I made before with a synthesizer, and you could just play. So there is a hosted AUV3 plugin, which is connected to an outside NanoKey Studio keyboard, and now we have keys coming in from the computer. The keys are coming to this synthesizer. It started as a sine synth, but it's not anymore. So when you go inside it, you can see these modules here. They come from these bundled modules that are still evolving, still very simple, no UI. But there is an oscillator, a filter, an envelope, chorus, and a stereo delay. So let's see, for example, the oscillator here has these 4 tables that come from this wave selector. I've shown this in another video. And whoops, that's the piano. Now what we're playing is actually this. Okay, so what generates these waves is this table oscillator, which I've shown before, and it's being modulated by a sine wave. And here are the 4 waves that we're playing. So after the oscillator, we have our filter, and here these 2 scope FFT components are comparing the output from the oscillator before being filtered with after filtering. So let's see. Oops, again wrong. This one. You could see here after the filter, it was going up in frequency, and then it came down faster than it went up. So when we go inside the filter, we see there's a 3-second attack and 1-second decay. This is our ADSR, and that's modulating these filters. Oops. So we have 2 filters at the moment. They're like 12 dB low pass. So these 2 together make a 24 dB low pass filter. So you can look at your chorus and stuff. Just not going to explain this now. And this stereo delay has some delays that keep going around in a loop between left and right channel, just to make it sound stereo. Okay, so what I want to show is how, like here, you have your filters playing audio, but we might want to actually look at the response of these filters to see if either to learn and to see if it's working well. Also for me, for debugging, it is quite useful. So I'll start a new schematic to show you how to do that. Okay. There's some new components that allow you to do this, and some changes to some existing components. What allows you to plot FFTs and waves is the wave show component, and you can see here you don't actually see the components you need. because this menu is like a context menu. So you have to create your custom instrument, and when you go inside, you will see lots of components. In the future, they'll be grouped in categories to make it easier to find them, because the list is getting quite long. But the wave show component is the one I want to show in this video. Okay, so here is wave show. Now this component has a wave, which is that W connector that comes in, and then it will show it. Now we want to run kind of code, except this is visual programming, but it's like compiled code. And this component here, show the labels here, will when it receives a trigger in this run input, this green connector means a trigger, it will run some code that's compiled from what comes to this input. Like for example, if we had a sine wave, a phasor and a sine wave. Sine wave works with a phasor, which gives it an angle. Okay, so this would be a simple compiled schematic. The purple stuff gets compiled, and we need to run it. So I'm going to put a trigger button, and when you click on it, you should have a sine wave, except there's no frequency there. This phasor needs frequency. So we need to, I'm going to type a frequency. Now there's two types of float numbers you can use. The purple one is for compiled, and float is for messages. And so actually this isn't the one we want. We want this purple one, so that we can connect it to that phasor. And let's give it a frequency of, let's say, 400. And now when we run the codes, we have a sine wave there, even though it's very, very low, but we can multiply it. There's a molt. So I'm going to multiply, let's say, by 10. Now it will be bigger. Okay, so that's our 400 hertz. We could go double that, 800, whatever. Now, you notice here that when we, every time I run this, the start is in a different angle, because we're not resetting the phasor. The phasor needs to be reset to always start at 0. Now when we, oh yeah, this trigger button has two trigger outputs, one when you press down, another one when you release. So I'm connecting it to the down event, and when this run component runs, it sends a trigger before it runs, and another one after. So before it runs, I'm going to reset the phasor, and now it's always the same. I'm pressing many times, and you can see here the phase stays the same. So instead of typing frequency, we can use a knob, and set our knob to go, let's say, from 100 hertz to 1000 hertz. And here we can connect to this compiled float, and it will receive the float message, and it will store it in the right place in memory. So now nothing's happening, because each time we change the frequency, we would have to trigger a run. But these float events, they're also triggers. They're like triggers with a payload of a float value, so we can actually connect there. And now when we change the frequency, it also triggers to run these compiled codes. And you can see the frequency going from 100 hertz to 1000 hertz. We could also look at this with FFT, running an FFT on it, which shows you the frequency graph. And this is how it looks. Now you can see the peak of the sine wave going up as we increase the frequency. This is showing dots because the resolution changes because this is logarithmic. You have lower resolution at low frequencies and higher resolution at the higher frequencies. Also, I might not need to multiply. Okay, so now you see. Okay, so this wave show also has another that F input, which will show a vertical line at the pitch. So like horizontally, we're working with pitch, where that line there represents the pitch of a middle C note, and this is going to have labels in the future. The second line is a C5, so 1 octave above, then C6, C7. Now, because we want to work with the pitch, I'm going to make this knob go from let's say 40 to let's say 60, which is middle C, to 3 octaves above, which should be 96. Each octave is like 12, so 72 would be 1 octave above. And so this should take us to this note here, middle C, to 3 octaves above. And so let's see, so this knob now goes from 60 to 96. But our compiled circuit takes frequency, so we need to convert float. There is P to F, and this converts. So 40 is 261.62. That must be the frequency for a middle C. And now we go up, and that must be the frequency for that one there. So this pitch we could plug there, and now we see a yellow line. We're not actually running, we're not running there. Now we're also running the compiled code. And okay, nothing's happening because I didn't plug this float, this frequency. I plug it to there to change it. And okay, no, I need to plug the frequency. That was the pitch. Now frequency. Yeah. So now we can see the yellow line is following the peak of our sine wave. And if we go to wave, we can see the actual wave. Okay, so this would be for sine wave, but if we want to show the response of a filter instead of our sine wave, actually I'm going to delete it. So now we would have a filter, and our filter has a cutoff and a Q, and I'm going to set it up. I'm going to type it. Let's say we want a cutoff of 400 and a Q of let's say 5. So for our input, what we need is the impulse component, because we're just trying to find the response of the filter. And so let's see. So now we connect this. Here we're going to have to multiply because we don't have a wave. We want to find the attenuation of at each of these frequencies. And before we run, we also need to reset our impulse, because the impulse will be just first sample at 1, and then it will be all zeros. So before we run our code, we will need to reset the impulse. So now, why? Okay, so now we see it ran. It got the impulse goes through the filter, and it generates this wave. The wave is not changing when we change the knob because it's not actually plugged. So if I plug the frequency, okay, so now we have here pitch between 40 and 96. We have here converted to frequency, then it goes to our compiled circuit, which the knob is then sending a trigger to make it run. Trigger comes out to reset our impulse each time it runs, and now we can see the response of the filter in the time domain as we change the frequency. Okay, so the way we see this in the time domain, if we want to know the frequency response of this filter, we now go there to FFT and we'll see. Okay, so this is going at 12 dBs per octave, like for example, I'll show here. If from minus 20 it goes to the next octave, it's like minus 12 dBs below that note. So that would be C6 at C6, or the frequency corresponding to C6. It would be there, and the 1 octave higher would be there. If we would want this to be like a 24 dB low pass filter, we could put two in series and connect cutoff, connect our Q, and now it's a steeper filter, and now again you can see from there to there it's like 20 dBs, so this is going like 24 dBs. From there to there is like doubling frequency or adding 12 to pitch, so it's like an octave. So this is 24 dBs per octave. Okay, so one more thing we can do here is, instead of using this knob to control frequency, there's also a new component, which is this drag XY, and if we show the results, so there's, for example, this is your X coming out, goes from 0 to 1, and this is our Y, doesn't change much in X. In Y goes from 0 at the bottom to 1 at the top. So let's say if we would want to use the X to control the frequency that we're currently controlling with this knob, we would want it to go from 40. We're going here from okay, here we're going from 60 to 96, but this plot at the moment is going from 40 to 100. In the future you'll be able to actually change the minimum and the maximum, but for now we want from 40 to 100 is a range of 60 in pitch. So we're going to multiply our 0 to 1 on X by 60, and then add 40. So instead of going from 0 to 60, it goes from 40 to 100. And now this value will go to our pitch to frequency, because here we're working pitch, but we want frequency. So let's see. Okay, so this would be, and now instead of going from the knob, we go from there. No, that did no, not from there. We want the pitch from there. Let's see, from beginning to the end. Yeah, and we also want to trigger a run. Now this drag XY has an X, a Y, and when it changes, it sends a trigger there. So we'll use that to trigger the running. And now we see this drag XY controlling the frequency with X. I'm going to make this lower, even though this would be correct with the 0 dBs set there, but because we can't scroll at the moment, we can scroll up and down, so I'm going to lower it so we can actually see it. Okay, so now we could connect the Y to control the Q. We would do a similar thing, multiply by the range of the Q we want. Let's say we want to go 5 in range, and I'm going to add 0.5. So this should go from 0.5 to 5.5 and plug it to Q there. So now we can move our Q up and down, and frequency left and right. You can always show this on like a separate window, and this drag as well. So let's see, there and there. So now we can see, and we could also show the wave rather than showing the FFT. For the wave we should actually multiply it, but yeah, okay, I'll do that, multiply by something bigger. And let's see, okay, so this would be like similar thing. So this would be like a high cutoff, a low cutoff with high Q with low Q. Let's see that in FFT. So low cutoff, high cutoff, high Q, low Q. Okay, so the idea then for the future, it's like you have these green connectors which are used to place controls on the front panel. Like for example, to place this knob on the front panel, you would just plug it there, and then you see it there, and if it was still plugged, you'd be able to control stuff. But this yellow will be for building UI, and there's some components which are like a H stack. You would be able to put your drag and the wave together horizontally, or you could have a V stack where one would be below the other, or even better, you could have a Z stack where you could put this in the background and this one just above it, and then you would be able to control to do the dragging on top of it.